In this episode, we ask the question, how are optical instruments verified and validated on the ground before flight? Hey, Josh Bernstein here. I'm on my way to the Smithsonian Astrophysical Observatory. The Smithsonian Astrophysical Observatory, or SAO, has a number of buildings in Cambridge, Massachusetts. This 7,000 square foot facility is where engineers design high-tech instruments for space orbiters and telescopes. I've arranged to meet with the engineers who design and test satellite optics in the clean room. Okay, going into the clean room, which means gotta get clean. So, first step coming in a clean room after you've cleaned your boots is to clean the soles by stepping on the blue tape. Come on in. Come on. Step on the tape. Good. Yes. Yes. Get Rob. Yes, of course.
Oh, thank you very much.
SAO engineer Dick Gates helps me put on the gear.
All the way over. Most people do one at a time. I'm impressed.
Dick instructs me to put on gloves, a smock, booties, a hair cap, and face mask so we can keep contamination levels low around the equipment inside. The fun part is actually not that I have to put on all this stuff, but my crew will too.
How's my hair?
Looks good.
Looking good.
And now you can put on your mask.
All right, we're going in. Once we're all suited up, I meet Chief Engineer Lester Cohen. For 15 years, Lester and his team have been involved in the design, fabrication, and testing of the JWST Optical Telescope. They have now finished the design and are in the process of assembling ground support equipment optical assemblies called piston sensors, which will be used during the cryogenic testing of the Pathfinder at NASA JSC. The Pathfinder is composed of the center section of the full telescope that was built to be tested in the same manner as the flight structure in order to minimize risk when testing the flight telescope. Scheduled to launch in 2018, the JWST will look deep into space to gather data with the goal of revealing how the earliest galaxies were formed.
Now, one of the key issues with the telescope mirrors, if you remember Hubble, it wasn't focused properly.
Lester explains that in 1990, the Hubble Space Telescope was launched into low Earth orbit. Shortly after it was launched, astronomers noticed that the images coming back from Hubble were not perfectly focused. The problem was its optics. Hubble contained a 2.4-meter mirror made from glass that had a spherical aberration, and therefore wasn't focusing precisely. Well, that can't happen with JWST because its mirror system can be refocused on orbit, but other errors can occur. The tests that will be performed at NASA JSC in a cryogenic atmosphere are meant to ensure that there aren't equivalent problems on orbit. To verify that JWST's mirrors can be realigned successfully, engineers have built the Pathfinder Telescope, a non-flight replica of the telescope's center section or backplane. Several mirrors and 30 piston sensors will be attached to the Pathfinder, and the entire structure will be brought to minus 400 degrees Fahrenheit to replicate the cold of space. When JWST is in orbit, its temperature will change small amounts, perhaps 1/4 degree Fahrenheit between observational positions. NASA scientists do not want this small temperature change to affect the performance of the telescope more than planned. It is this specific test at cryogenic temperatures that the piston sensors will be used in conjunction with the two PMSA backup mirrors. Lester shows me one of the piston sensors, then introduces me to his colleagues who are calibrating it with an interferometer. I can see you because you don't have facial hair. Nice, okay.
We're adjusting the base plate to be aimed correctly, so it points this whole structure to the interferometer.
Okay.
So that's the first step that we do. Vlad's developed all this software to tell us where we need to point it.
Okay.
And then we adjust each one of these screws.
You manually adjust the screws?
You manually adjust the screws. You actually go and you unlock them, and you use an Allen wrench and you count the number of turns.
When the piston sensors are aimed at the interferometer, another engineer checks that the alignment is accurate. He sends a laser beam through the piston sensor's lens.
See how there's a small dot there?
I see that.
So the interferometer is focusing to this dot.
Yeah.
Then the light expands out and goes through the piston sensor.
So this beam is coming through the lenses, and then the goal is for it to come back on itself.
It comes right back on itself and all the way back.
And is red on that machine over there.
That's right.
Risk reduction is one of the team's top priorities, as the 30 piston sensors will help them monitor the predicted change to the structure's shape and make sure it is in predicted limits.
So we're basically checking the accuracy of the alignment of that piston sensor. And what is it you're seeing?
What I'm seeing is this curvature inward, which is the astigmatism, just like in an eye.
Yeah.
And we can analyze that.
Think of a potato chip.
Yes.
Yeah. Or a saddle. It's that kind of shape.
Okay.
We can capture a measurement.
Yeah.
And we can analyze the amount of astigmatism.
So far, all the piston sensors tested have passed with flying colors.
And so the next step for these, if they all pass, is they get brought to Johnson?
Yes, we put them in containers,
Yeah.
we ship them to Johnson, and then we assemble them at Johnson.
And then they get the deep freeze.
Yes.
At Johnson Space Center in Houston, Texas, the Pathfinder's performance in extreme cold will help engineers evaluate problems that might face the JWST's backplane in space and solve them while the structure is still on Earth.
When we test the flight structure at Johnson first, we want to make sure there's no gotchas, because we're going to do the same test but with the real flight telescope at Johnson in 2017.
Yeah.
That's why we spent a lot of time and money on that Pathfinder structure.
The answer to our original question, how are optical instruments verified and validated on the ground before flight, is with a very thorough methodology. Defining problems, designing solutions, and testing them for the physical realities of space is a big part of what these highly trained engineers do every day. As a result, when the James Webb Space Telescope finally launches in a few years, everyone hopes that it will perform perfectly, giving us greater insights into the origins of our universe.